Okay, everybody, welcome back. We're going to go ahead and get started. And you are in the right place if you are here for Introduction to Surface Water Treatment. It looks like we have lots of people from all over the map. So if you've been to one of our webinars before, welcome back. If you're new, welcome. And if you're so inclined, you're welcome to share where you're attending from in the chat. Sometimes that's nice to see. Everybody's from all over different places. Okay, so I'm really glad you decided to join us. My name is Lori Krings. I'll be moderating today. And let's look a little bit at our plan for today. So we are coming to you from the Center for Technology and Training at Michigan Technological University in Houghton, Michigan. And I'm excited to welcome back Greg Pearson and Daryl Gotham with us today as our instructors. Greg is a water and wastewater trainer here at the Center for Technology and Training at Michigan Tech. And Daryl is a research engineer also here at Michigan Tech. And we're really looking forward to what both of you have to share with us today. Let's talk a little bit about a few housekeeping things, a few key announcements. So for today, we do have closed captioning available if you should need it. And if you want to just look at the bottom of your Zoom window, you will be able to see like something that says CC or live transcript in your bottom toolbar there. And you can select to show subtitles or to view a full transcript. But if you have any questions or any issues or really need some accommodations or have difficulty accessing the content, please do contact us or just send me a message. And I'm happy to help you through that, or we're happy to help you figure something else out for that content. For anything, if you have any questions, please do go ahead and put those into the chat. I'm also going to be monitoring the Q&A. So if you don't want to use the chat for a question, please go ahead and put that into the Q&A. And I'll be paying attention to both of those as we go forward and holding questions for the Q&A section at the end of today. Please know that I'll be paying attention to those. And we will be also having polls today. So if you have any trouble viewing the poll questions, it could be that you have a Zoom pop-up setting that you might need to fix. If you find that that is not something that you can get around, you're welcome to put your poll answers right into the chat. That's fine too. And as we get started here, when I'm done walking through today's plan, I will go ahead and put the slides into the chat for everyone. And I'm going to share it in two formats because sometimes people have trouble opening them. I'll drop a PDF in, and if that doesn't work for you, I'm also going to share a link to the slides. If neither of those work for you, please do just message me and let me know, and we can sort that out. There will be a recording of this training that will get sent to you when we send out the certificates. So know that that will be coming to you when the certificates go out. And that comes in, give us about 10 business days to get that out to you. We will be taking about a 5 or 10 minute break later in the session today. And like I mentioned before, we'll be having Q&A at the end of today too. So if you happen to have any questions after we close the session, you're welcome to email us at ctt@mtu.edu. And if anybody needs a certificate of attendance for today, you don't need to take action today. The action you need to take will be tomorrow on day 2. And I will be sharing a link that you need to complete an evaluation. And that's basically how you will get your certificate. So if that matters to you, please pay attention at the end of the session tomorrow and look for that link. But if you have any questions as we go, I'm happy to answer those. And I'm excited for us to get going. So what I'll do is I'll turn it over now to Daryl, who's going to start us off. So thank you, Daryl. The floor is yours.
Thank you, Lori. So I appreciate everybody attending on the day here after the holidays. Hopefully everybody had a good holiday weekend. A little bit about the Environmental Finance Center Network for those who maybe aren't familiar. This is provided this training is provided through the Environmental Finance Center Network. We here at Michigan Tech are part of that. We provide training and technical assistance to water and wastewater operators throughout the country. As you can see, we've got there's 10 different regions in EPA, and we closely follow those regions. We are located here in EPA Region 5. This training, however, just to give you an idea how it's a nationwide reach, it's part of a training that was requested by the state of Georgia. So we're providing it, but obviously that's not within our region. So, so here's the Great Lakes Environmental Infrastructure Center, serves those states in Region 5. We've got our contact information, phone number, website. So if you're so inclined, please reach out to us. So what are we going to cover today? So I'll be covering surface water sources, some different information about surface water. After my presentation, Greg will cover the treatment processes: coagulation, flocculation, sedimentation, filtration. So Greg has the bulk of the training today. So let's move on. So what are surface water sources? So surface water sources are, lakes, rivers, streams. How are they different from groundwater systems or sources? Well, they tend to have a lot of suspended solids, and that's due to quite often to the runoff that we experience. Water gets into our surface water bodies by going overland, picks up things. You look at lakes and rivers, quite often we see microbial contamination in those, and most groundwater sources typically don't have that due to the filtration that soils typically provide for the groundwater, and it's usually not a very good environment for microbes to exist in groundwater. So surface water is also the water quality quite often varies, and that's due to it's quite often due to the precipitation, runoff, how land use how it's used, and we can quite often see major changes in surface water, from relatively clear summer shallow rivers to rivers that are full of sediment and milky and brown, potentially in color due to spring rains, or up here in northern Michigan due to snow melt. So it's surface water sources change quite a bit, and they vary from one to another. So for both groundwater and surface water, watersheds are very important, but quite often with surface water, they're even more, they have the ability to change the quality of our source dramatically in a short period. So if we look at some of the examples on here are failed septic systems in a subdivision. Quite often that'll go through the groundwater to get to the surface water, but it also can nutrients and things like that can affect our quality of our surface water. Oil and chemical spills. That's obviously something that can get directly. They can run or be directly deposited into. If they get into a storm sewer or something like that. So there's we've got to look at all sorts of things when it comes to how to protect our watersheds when we're using surface water as a source. And so we have, we also have agricultural, whether it's land application of fertilizer or pesticides and herbicides, that all can get into our watershed. So we group these together. The potential sources of contaminants for our surface water into three main categories. So point source pollution is probably the most obvious one. It includes things that get directly discharged. It could be from a wastewater treatment plant. It could be from an industrial operation. And those are usually pretty easy to see. I quite often, connect those to the pipes, the idea that the pipes that actually are putting stuff into the surface water. And then we've got a creative name for the things that aren't those. And so if we call the others point source, we're going to call these non-point source. So it's pretty much everything else. And it's the stuff that runs off from a farm field. It's those areas that it's hard to actually pinpoint what that area is, where it's coming from, what's the source of that problem. So could be urban storm drains that can be all add up to what we consider non-point source. And as I said, that's a little harder to put put a source to it. Quite often it could be just water running off a farm field. And then the last one is air deposition. So that's the thing that comes to mind when we talk about air deposition is acid rain was a huge news topic back in the 80s and the early 90s. So that's one of those ways that we can get water that our source water can be impacted from things that are in the air. And we'll go into a little bit more detail about what acid rain is later in the presentation. So I think I mentioned a little bit, rivers, are probably the most volatile. They have the ability to change very quickly. Things can impact a river source almost immediately. If we look at, we have an oil spill that goes directly into, could go directly into our source water intake. All of these things, we mentioned before, I talked about fertilizers, herbicides, pesticides. Due to the flow of rivers and, the limited size of the area that we typically collect our water from, rivers and streams are I call them flashy. Things can change in quite a hurry. I guess if we look at some of the rivers and the floods that happened in Texas, how quickly things change there. So what an important thing to consider when we're looking at source water or surface water sources is the idea of stratification. So we've got a water body, and the temperature changes as typically it's colder at the bottom and warmer at the top, and there's things that can cause that water to flip over. And so if we look at this, we've got these crazy names: epilimnium, metalimnium, hypolimnium. It's based off the idea that limnology is the study of inland waters. And the nomenclature comes from Greek or Latin, with epi meaning above, and meta means beyond or after, and hypo, which means under or below. So we've got the three different layers. And this is typically the case when we have deeper water sources. If we were to look at a lake that was, say, only 10 feet deep, we're probably not going to see these different layers, because the wind would allow for some mixing of those layers, and so they're not nearly as identified. And the sun is could potentially penetrate to the bottom, which which could cause the temperature to be a little more consistent throughout. So, so the epilimnion is the area from which water systems draw water, unless there's an issue with algae. If algae is an issue, then they're likely going to collect it from the metalimnion, and that's the area which the temperature changes rapidly as it gets deeper. And then with the hyponymnion, that water is colder, it's denser, and it's typically considered to be less quality. So I'd mentioned just briefly the idea of the turnover in lakes and reservoirs. Quite often what you see is in the fall, as the air temperature goes down, the water, there's times in the fall when the water temperature is actually greater than what it is in the air. And so that air will cool the water. And as that cools the water on the top layer, and typically colder water is denser and it wants to sink. So we see this turnover. So we start typically with the normal idea is that the warmer water is on the top and the colder water is on the bottom. But as the top water cools, it wants to sink. As it sinks, it brings up water from the bottom. So we get this turnover, causing the colder, denser water to sink to the bottom. And that'll stir things up. It can cause issues. It could create turbidity concerns. And that process can also happen in the spring. It's possible for areas where you've got ice on water, that can cause this process to happen as well. Another thing to expect if we've got surface water is the potential for eutrophication. So warm, slowly moving water, along with nitrogen and phosphorus, make for environments that are conducive to this process. So that's why, it's, to me, one of the things that comes to mind is this eutrophication process is a common reason why we'll find sewer systems along rivers and lakes to prevent the nutrients from getting into the water and causing these types of things, the nitrogen and the phosphorus nutrients. So when the algae dies off, it reduces the amount of oxygen in the water, which kills the aquatic life. We'll often see fish kills when this happens. And in general, it's just the water quality is not nearly as good as it had been before the algae blooms. These things can also release toxins. I know in Michigan and Lake Erie, we have concerns quite often in the summer with harmful algal blooms. And that's when algae or cyanobacteria, which is considered blue-green algae, grow out of control. And then when they die off, they can release these toxins. If a system has a reservoir that they start to see algae growth starting up, they can treat that with things like copper sulfate, which should hopefully stop or reduce the toxic bloom. So I mentioned a little before, watershed management is important when it comes to surface water. So because a lot of the things that happen out in that watershed will end up in our surface water, we really need to make sure that we take advantage of any opportunity that we have to limit the things that come in, whether it's if we've got sediment that comes from a farm field that was plowed up, or if we've got things that come off of plants and stuff like the treatment plants. So you need to, in a watershed management plan, you need to identify the area that will ultimately serve your surface water source. You go back in this case, we've got some smaller sub watersheds. It's important to pick up all those little things and make sure that we're looking at what might happen in those areas. In the Safe Drinking Water Act, it takes a barrier approach. So the idea is that we're going to do a bunch of little things that hopefully result in the best quality and the safest water that we can provide. And this is the first way that we can go about that. So the idea here is that all these little tributaries, all this runoff comes into our surface water body. And because it travels over ground, there's a lot more likelihood that the things that can hurt us are going to end up in the water. So waterborne pathogens, that's why we need to do filtration and disinfection to either remove or to kill off those microorganisms. The only problem with that is that as this water flows across the ground or it gets to our source, our surface water source, it picks up organics. And when we disinfect, when we add chlorine, we're going to form disinfection byproducts. Now, our processes can take out hopefully as much organics as they possibly can, but usually with a system that has a lot of natural organic matter in the source, we're going to find elevated levels of disinfection byproducts. So in this case, we've got a cattle ranch. For instance, the water from that cattle ranch flows into our surface water and could potentially add some pathogens. So natural organic matter, I mentioned that previously. It can also add to if that makes it through our treatment system, it can add to the growth of biofilms out in our distribution system. And when we've got that natural organic matter out there and it starts to grow on the pipes out in our system, it's an easy place for bacteria to live. That biofilm is it's a host. It's a great place for pathogens. So if we can take all that stuff out before it gets out into our distribution system, we'll be that much better off. All right, so we're going to look at some of the water quality parameters that are involved with our source water, such as pH, alkalinity, some additional chemical parameters. We're going to look at some of the pathogens that we'll see out there, and what kind of factors influence our surface water: turbidity, suspended solids, and some other water quality factors. One of the biggest ones that we deal with often is pH. It's important for a lot of different processes that we do in a surface water treatment plant. So if we've got a water with a low pH or a pH below 7.0, it's considered acidic. And acidic water can cause corrosion. So it's important to remember when we get into why this is a balancing act. So acidic water can lead to corrosion. And on the flip side, water with a high pH or an alkaline or basic water can contribute to the scale formation inside of pipes. So, it can affect our fixtures, our plumbing. So, too high of a pH can cause problems, too low of a pH can cause problems. And it can also affect how efficiently we our processes are. It can affect our chlorine disinfection. And as I had said, there's some, it's a balance. We have competing compliance goals, and we need to try and meet multiple things and still provide the best water that we can. So a lower pH, which would be an acidic water, our chlorine disinfection process works better if we have a low pH. But the problem with a low pH water is that it's also, as I had said, it's likely to lead to corrosion. So that can affect our lead and copper. So we're balancing the idea of we want to have good chlorine disinfection, but we don't want to have issues with lead and copper. So as I had said, when we're talking, I briefly mentioned acid rain. So normal rain is in this range here, and acid range is just slightly more acidic. It's a 4 to 5 on the pH scale. So another one of the important things to consider with surface water treatment is alkalinity. And alkalinity is important because it's the resistance of water to change in pH. It's got compounds that buffer and resist that pH from changing, and that can be helpful in a lot of different ways. If water has a low alkalinity, it's got a greater potential to be corrosive because it's lacking that buffer to prevent the acids from leaching or from leaching electrons from the metals. So when we go to determine what the alkalinity is, we get into our high school or college chemistry course, and we get to do a titration. So the idea is that we're going to take our water sample and we're going to add acid to it drop by drop until the pH is reduced to 4.2. Typically with that, we'll see it was a color change. So you've got a certain color, and then you add your acid, and then that color goes away, and that will give you an indication of what your alkalinity is. And as it says, the method is drop by drop. It's called titration. So we're going to titrate our sample to determine what our alkalinity is. And as we said, it helps to prevent corrosion. Our alkalinity is it's that buffer that helps and it helps prevent corrosion. Hardness is another thing that comes out, and it's hardness is typically more of a concern with groundwater sources because it involves all those dissolved minerals that come in through the water. Typically, source water systems don't start with high hardness, but it's important to have some hardness when it comes to preventing the leaching of lead and copper. So it causes hard water will cause scale to build up on pipes, and that's important when it comes to preventing the leaching of lead and copper from pipes. So what are the different levels? So what classifies? So a soft water is less than 17.1 parts per million. Slightly hard is from 17.1 to 60, moderately hard 60 to 120, and hard water is 120 to 180 parts per million. So once again, we had, it's that balancing act. We want to have some, but we don't want to have too much. So I think we talked about suspended solids earlier. So now we're looking at dissolved solids. Dissolved solids are things like iron, manganese, and fluoride, and they can affect the aesthetics or the taste or odor, the quality of what our residents see as the quality of the water. And it can be difficult to treat for dissolved solids. EPA established, they have these for a few different, contaminants, and they consider them secondary maximum contaminant level. So they're not enforceable, but they're guidelines, for contaminants that might cause aesthetic problems like taste, odor, and color concerns. And as I had mentioned, iron, manganese, and fluoride are some of those that have secondary MCLs. And so for total dissolved solids, the secondary MCL is 500 milligrams per liter, 500 parts per million. So this chart just shows you some of the different, Ingrid, let me get my head out of the way. So this chart shows some of the different, what effects can happen at different quantities or concentrations of total dissolved solids, TDS. So there's quite a range there, and typically the way things work, we want to be somewhere in the middle. Both sides, being on either side or the other is usually not a great thing. So when TDS is made up of salts, it can increase the conductivity and corrosivity of water. But also, if you've got a very low TDS, that water can be corrosive as well. So that's why I say that it's best to be somewhere in the middle, usually for most of these parameters that we're looking at. So why would we treat surface water? I myself, I like watching these survival shows, and it's funny because it seems like we're always looking for a way to treat water. Typically on those shows, people are drinking surface water because that's what it's available. We don't see a lot of people, digging wells to get to groundwater. So, and one of the most important things it seems like they have is fire, so that they can boil their water, so that they can make it safe to drink. Usually the biggest concern they have in those situations are the pathogens, because those are the things that typically can do immediate, they're acute issues with those versus a long-term. So hopefully they're not in this survival situation for years. So they look at what can they do to treat the water, and that's getting rid of the microbiological pathogens, the bacteria, protozoa, stuff like that. We also treat, for more of the long-term issues. We're going to treat for the inorganics that can quite often are metals, the organics, the radiological stuff that's out there, whether it's natural or if it's radiological stuff that's man-made. So yeah, it's definitely we treat it, for health concerns, to make sure that we're providing safe, reliable water to our constituents. So EPA's group has 7 different groups of regulated contaminants for the Safe Drinking Water Act. There's the microorganisms, those are the bugs and things. There's disinfectants, which are things that we add to try and make the water safer, and whether it's chlorine dioxide, and those things, we still need to regulate them because we want to make sure that they're not getting at concentrations that would be of concern. As a result of adding disinfections, we have disinfection byproducts, and those are caused when we've got organics, naturally occurring organics in the water, and then we add chlorine. So that results in the production of disinfection byproducts. As I mentioned, we have some inorganic contaminants, which are usually minerals or metals. Arsenic and mercury are probably a couple of the more prominent ones that come to mind. And those could be result of contamination. They could be naturally occurring. Volatile organic contaminants, or VOCs, are typically man-made. Quite often, I like to think of those as things like gasoline and stuff like that. The SOCs, or synthetic organic contaminants, are substance that the EPA has already banned. You shouldn't be using them, and they're associated with herbicides and pesticides. And then radionuclides can be either natural or man-made. Radium could be radon, things like that. And then, what do we have to look forward in the future? When it comes to surface water, the regulations are change very quickly. There are a host of different things that we've already looked at, that EPA already regulates. I think if I look at these numbers as a total, there's around 87 different things that we look at that are EPA regulates. But there's 86,000 that are in the inventory and aren't being regulated at this point. Some of the ones that are obviously in the news a little more are the PFAS and the microplastics. Pharmaceuticals and endocrine disruptors are also examples of emerging contaminants. It's gotten to the point where there's entire, EPA, I believe, and many of the states have people dedicated to the idea of these emerging contaminants, and their job is to make sure that to keep an eye on and follow and make sure that they're aware of what the next thing coming is, because we have to figure out how to treat for them, or how to take them out of the equation before they get there. So if we're doing it in our watershed, or if we're doing it as part of our treatment, if we're doing it in the distribution system. So, that brings up the whole idea mentioned previously, and of the multiple barrier approach, the multi-barrier approach. It's, and we started in this discussion, we started with source water protection and watershed management. As we go through this, Greg will talk about later on here today about water treatment processes. That's a second barrier that we have to try and make sure that our surface water is safe to drink. And then we're going to look at we look at water quality testing. What do we do to ensure that it's coming out the way that it needs to be. And finally, things that we can do in the distribution system to make sure that we're providing safe water to our customers. All right. So this is Greg's topic coming up this afternoon, and then I think we're on to our first poll. All right. I see Lori's brought the poll up for everybody. So the question is, what is an example of an impact of non-point source pollution? Is it A, wastewater effluent discharges add total suspended solids to a stream? Is it B, precipitation causes water to flow into rivers, lakes, and streams? Is it C, nutrients from agricultural runoff leads to eutrophication in lakes and reservoirs? Or is it D, all of the above? I'll give everybody a couple minutes to get your responses in. All right, so we're getting there. We got over 100 responses. A moment or two here for. All right. All right, I haven't seen a response in a little bit. Lori ended the poll, so so our responses, it looks like we have, that's pretty close. We have 45% or percent of the people saying C, nutrients from agricultural runoff leads to eutrophication in lakes and reservoirs. We have 41% saying D, all of the above. We've got 11% with B and 3% with A. So, pull that poll. All right. So it's kind of tricky. So the answer is C, and that's so impacts of non-point source pollution. So wastewater effluent discharges, adding TSS to a stream. Wastewater effluent discharges would be considered point source pollution. So that rules out A. Precipitation causes water to flow into rivers and lakes and streams. Yeah, that could be considered, but it's not actually, there's no impact identified. So, under ideal situations, we have precipitation that flows, but it doesn't have an impact. And then, so that'll leave C, which is, nutrients from agricultural runoff. So agricultural runoff would be considered non-point source. And then the impact is the eutrophication of our lakes and reservoirs. Non-point sources include general runoff from agriculture operations and stormwater that bring nutrients into water bodies, increasing the growth of algae. So, all right. So next up will be Greg. I see Greg's looks like he's ready. He needs to unmute himself, I think.
Hello, Daryl. Thank you for that excellent presentation.
Thank you, Greg.
I'm so glad that Daryl joined us. I'm not sure how many of you know, but Daryl has a background in working as a regulator in a primacy agency, and he's had a lot of experience managing water and wastewater plants. So I'm so glad that he joined us today, and thank you for that excellent introduction that segues us right into the surface water treatment process. And welcome to everyone. I saw a lot of posts in the chat about where people are from, and I appreciate all the people joining from all over. And I see some Georgia operators as well joining. And this particular treatment class was made for Georgia, but of course it applies to all water systems across the United States. Lori, thank you. I'm going to let you be in charge of polls. And should we plan for a break about 2:30? You think that works?
Sure, that sounds good to me.
Or 2:20 maybe?
Mhm.
Okay. So we're going to move into the water treatment process, and we're going to be looking at 4 removal processes basically. First of all, we begin with coagulation. And basically what that is, we're adding a coagulant chemical, which is going to neutralize the charge of particles. Particles tend to exist in raw surface water as negatively charged particles. We're going to talk about that more, but the coagulant addition destabilizes those charges so they can begin to clump together to make larger particles. And in flocculation, we're continuing to build the size of our particles, which we call floc. Those particles that are an agglomeration between coagulant chemicals and particles that are already existing in the water supply. We make them heavy enough so that they'll settle in the sedimentation part of the treatment train. And finally, we go to filtration, and this is called the conventional treatment process. In filtration, we pass water through some type of granular media to remove those floc particles that wouldn't settle out in sedimentation. So the filters have a little more difficult job. In sedimentation, it was those big, large particles that wanted to settle out. But what's sent to the filter is the very smallest particles that wouldn't settle out. We're going to look at each one of these as we go along. There's another type of process that eliminates the sedimentation step, where it goes directly from the coagulation, flocculation process right to the filters, and that's called direct filtration. You would possibly use that if you had a source water that was very low in turbidity, so that it wouldn't be overloading the filters with excess. If you're treating a very turbid river, for example, you'd have so many solids, such a high amount of particles to filter, it would quickly overwhelm the filter. But for very low turbidity waters, you can get away sometimes with direct filtration. There's also another related process that I'll just mention here. We won't go into it too much, but slow sand filtration is another form of filtration where there's no processes preceding this. There's no coagulation, flocculation. Basically, in slow sand filtration, it's very slow for one thing. The filtration process is very slow, but um, you add water to the top of a layer of finely graded sand. And over time, over about a week, maybe 2, it develops this layer on top of it, which is a zoological film, which consists of all types of different microorganisms, bacteria and protozoa and so forth. They form a little layer on the top of that sand they call it a smooth deck. I believe that's some kind of maybe a German word for this zoological film. And that zoological film, it acts as a filter, and it does a lot of different functions. It strains the particles out. It captures them with the adsorption functions, and it also even has some microbiological actions. And so these work pretty well, actually. However, it's so slow, it would be impractical for a large city. Now we're going to kind of build a little bit on what Daryl was talking about, the reasons to treat and all the different sources of pollution that can enter a body of water. But what goes along with this discussion is particle size. And if you look at this chart here, you can see the first 4 types of particles in that middle column: gravel, sand, and fine sand, and even the protozoa, algae, and clay particles that are 10 microns or greater. they will all settle without treatment in a reasonable amount of time. Something like fine sand would take only 2 minutes to settle, whereas a clay particle of 10 microns would settle in about 2 hours, which is a reasonable amount of time for these particles to settle out. Now, if we get down on the lower part of the chart where we're looking at particles that are 1 micron and less, these would take a long time to settle. At the bottom, we have a colloidal particle that's 1 nanometer in diameter, and it would actually take about 200 years to settle unless we provide some treatment. And so that's a big part of the reason why we are going to be engaging in the treatment plant process to cause those the smaller particles to clump together to form larger particles that can be filtered or settled out. Now, just to get some idea about sizes, we're going to explore sizes a little bit here. Now, particles between that bottom, that smallest particle, 1 nanometer, and 1 micron, they're generally classified as a specific type of solid, as a colloid. Colloids are very small, and there's a couple different ways to think about them. Colloids really can't be filtered with our standard filtering process. When we do a suspended solids test, we filter it through a filter, and it will have a pore size around 1 micron, but it's considered to really only be reliable to filter solids that are 2 microns and greater, and everything else passes through the filter. So the only way to measure those small colloidal particles is by a dissolved solids test. So these are so small they kind of fall between the size of suspended and dissolved solids. And just to get a little idea of the range of sizes here, 1 micron is 1,000th of a millimeter, and a nanometer is 1,000th of a micron. So a micron is also 1 millionth of a meter, and a nanometer is 1 billionth of a meter. So very small. A nanometer is almost to the size of an atom. There's different categories of solids, and we just mentioned dissolved versus colloidal, and some of these definitions overlap, and I want you to understand how they overlap when you see different definitions. So a dissolved particle, its official definition, it's a substance that's broken down into its individual ions or atoms, and it's evenly dispersed in the water. Like salt, for example, there's a bunch of ions, salt ions that are dispersed in the water when you dissolve salt in water. They're not a particulate necessarily that is considered a solid. They're dissolved, they're in ionic form. Another definition that we are using from a practical standpoint is, as far as laboratory procedures, we usually consider solids less than 1 or 2 microns as part of dissolved because we just can't filter them. So the filtering apparatus there at the bottom right of your screen, I'm going to explain that as well. But if we do a total dissolved solids test, we're actually filtering the water and looking at the water that's been filtered. We have to evaporate it and then determine by weight the solids that are remaining that weren't able to be filtered. And so generally the dissolved particles are actually smaller than about 1 nanometer. But because of the limits of our laboratory ability to filter those particles that small, a lot of times we have to do a dissolved solids test to measure those solids. Colloidal particles are generally between 1 nanometer and 1,000 nanometers in size, which would be the same as 1 micron. So between 1 nanometer and 1 micron is colloidal. And we can't really filter these, or we can't settle them in the treatment process either. They contribute to turbidity, though, which is the cloudiness of water. So we need to remove them and they can, turbidity can also contain microorganisms. So that's why we're trying to get rid of them. There's a couple of links here on this slide that you'll have in your handout here. There's some solids testing lab procedures that came out of the University of Georgia. So it takes you kind of step by step through TSS, total suspended solids measurements, total dissolved solids measurements, and so forth for water and wastewater. It's a useful guide. And also there's a good YouTube video that takes you through a TSS test. Now this apparatus you see here is for conducting a TSS test. So at the top of that flask, you would pour in a known volume of water, and you'd use a vacuum pump and filter those solids out of that water sample. And then you would take those solids that are captured on that filter and dry them and weigh them to see how many solids you have. And then you would end up with a concentration in milligrams of solids per liter of water. Now, the filtered water here, that would be used to determine the total dissolved solids, because that all the solids that can be captured are removed, then you'd have to dry that and then weigh the remaining solids. So just a little bit of insight when we're talking about solids there. If we also, we're going to continue a little bit with the size comparison here. On your screen, that ruler shows a centimeter scale on the bottom, and the white part of the ruler, and the 1, 2, and 3, those are centimeters, and a centimeter broken up into 10 divisions is a millimeter. 1 millimeter is equal to 1,000 microns, and 1 micron is equal to 1,000 nanometers. So a nanometer is very small, and we can look at some of the common objects here. A single atom, 0.1 of a nanometer. That's called actually an angstrom. And so we go to a whole different scale when we get down to the size of an atom. But this C60 here, it's a special atom a special molecule that includes 60 carbon atoms in a sphere. That's 1 nanometer. So when you're thinking about removing contaminants that are molecules or ions, like I think Daryl mentioned arsenic, for example, we're talking about needing to remove very small things. DNA to protein, 2 nanometers to 10 nanometers. So, and viruses, 100 nanometers. So some of these things are very small, and all the way up to bacteria here, 1 micrometer or a micrometer is where you have a bacteria. Those are all considered colloidal particles that will not easily settle unless we have treatment. And continuing on with this idea, why won't these small particles settle? It has to do with the ratio of surface area to volume. And I have some examples here for you, but the smaller the particle is, the more surface area to volume it has. I think that might be, from human experience, you would imagine a little mouse could jump off a 10-foot building and land, and it wouldn't hurt it a bit. But if an elephant did that, it would probably break its legs. And that's on a macro level. But if we go down to a very small level, I'll show you what happens here. First of all, we start out with a 1 meter cube, and I'm using all the measurements in centimeters so we can compare. But if you add up the surface area of all the sides of a cube that has 100 centimeters or 1 meter diameter, the surface area is 60,000 centimeters squared, and the volume is 1 million centimeters squared. If we divide the surface area to volume, we get 0.06. If we go down to a 1 centimeter cube, the surface area to volume becomes 6. A 1 millimeter cube, the surface area to volume becomes 60. So the parachute is getting larger and larger. And then if we go all the way down to a 1 nanometer cube, the surface area to volume is 60 million. So imagine if you had a parachute that was that was equivalent to 60 million times your weight. You could jump out of a plane and it would take you forever to get down to the ground. So a colloid of 1 nanometer has an extreme surface area to volume ratio. To make matters a little more difficult, these small particles tend to repel each other. Particles of turbidity or colloidal particles, they tend to have a negative charge. This is because primarily due to the clay minerals that are mixed in with the water source. And there's a little chemical process that goes on that causes them to be negatively charged. So they repel each other. So with colloidal solids that we're trying to remove in the treatment process, not only will they resist settling because of their size, but they also repel each other. There's electrostatic repulsion going on. So the process of treatment is going to have to do something to neutralize those charges so that these particles can actually begin to clump together. And that's what coagulation does. We add coagulant chemicals are positively charged, and they neutralize the charges of the negatively charged particles that are naturally in surface water sources. And then they can begin to clump together. They can attach to the positively charged coagulant chemical and make microfloc, and they can continue to come in contact with each other and grow larger floc so that they can settle. So if you add the positively charged coagulant, you can neutralize the charge. And kind of continuing on what Daryl was talking about, we can look at the kinds of solids that are found in surface water. If you were to take a sample of surface water and filter it and look at the kind of particles that are in there, you would see there's particles of silt, clay, and sand, and those are mostly from erosion and construction activities after runoff. You're going to find some organic matter. There's going to be some decaying plant and animal debris or organics that can create disinfection byproducts if we don't remove them. And as well, the same with algae and plankton, microscopic plants that grow in water sources. Also, you'll find some evidence possibly of industrial effluents, like PFAS. Daryl mentioned PFAS, wastewater effluents, and microorganisms, bacteria, viruses, and protozoa. Also, you may find some chemical precipitants, some microplastics and synthetic fibers, and you may find evidence also of different kinds of personal care products, like pharmaceuticals. You might also see herbicides and PFAS. Hopefully this doesn't happen to you, and you end up in the adding a car to the river. I think, Lori, wasn't this one we allowed you to drive? Was it?
I don't remember that,
Oh,
actually.
maybe that was me. That was
Yeah.
me. Just a little joke. So when we are adding coagulants, we're allowing the particles, the impurities, the negatively charged particles, and the positively charged coagulants to flock together. And this is a little image of what the flock might actually look like as it's forming. And I'll give you some examples here of some common coagulants that we use. One of the most common is alum. You know, the Egyptians 3,000 years ago actually used alum, or a form of alum. Alum can be found as a mineral in the ground, not in the refined form that we'd use it today necessarily, but they would add alum to pots of river water that they collected, and it would cause the contaminants in the water to settle to the bottom. When alum is added to water, it actually forms some hydroxides that are positively charged, and it also, because it forms hydroxides, it uses up alkalinity in the water. So that's one of the characteristics. It uses up alkalinity, So we'll talk about that a little bit more, but that's a very common aluminum sulfate, Na2SO4. Also, there's polyaluminum chloride, or PaC. There's different forms of it, but it's a kind of a form of alum where those hydroxides have already been formed. Ferric sulfate is a common iron-based coagulant. It tends to produce a denser flock than alum, but because of its denser, it can also make the sludge more difficult to remove. And finally, ferric chloride. These are probably the four most common coagulants that are used. Ferric chloride is the least expensive. It's actually a byproduct of iron processes, creating steel. So it's considered in a way kind of like environmentally friendly because you're using a waste product for a beneficial use. It's least expensive because of that reason, and it provides fast sedimentation, dense flock. It works well even in cold weather or cold water. But one of its main drawbacks is its corrosivity, and it can increase the corrosivity of water. And if you look at coagulants, you'll see there's a bunch of different proprietary coagulants. These are kind of the traditional, most commonly used. Uh, and when I say that, I mean looking back for the last several decades. In a way, that's kind of changing because there's new formulations out there. There's even organic types of coagulants that are being used. But in general, when you talk about coagulants, you're looking at aluminum-based and ferric-based coagulants. And we'll talk about some of these. I'm probably going to talk mostly about alum and we'll compare other coagulants to alum as we discuss this topic. There's different ways to feed chemicals. There's different types of feeders. The first is feeders that feed dry chemicals. It can be on the basis of the volume, where you'd have an auger or belt system that feeds a certain volume over time. And they may have some kind of a component that either shakes or mixes uh, the chemical in the hopper so it doesn't clump together, so it'll feed evenly. And so there's different things that can be done. For example, for coagulation, you could feed a powder instead of a liquid. That's not very common. Usually the solid forms of alum are liquefied anyway and fed as a liquid, but it's possible to do that. For adjusting pH at a treatment plant, you would feed um, some kind of a lime or soda ash. Most likely that would be fed as a dry chemical. And you can also feed powdered or granulated activated carbon as a dry feed. Sometimes those might be combined with water to make a slurry, but those are common ways to feed it. Dry feeding can also be done with a gravimetric feeder where it's actually weighing the chemical. And there's two methods to do that. The first is measuring the loss in weight of the entire mechanism as it's fed. And so the controller will sense how much weight are we losing and how can I adjust the feeding speed to make sure that we're losing a uniform weight according to the desired feed weight. And you can also have a system that measures the chemical going out on a belt, like a conveyor belt type of a arrangement where it's constantly comparing the weight on the belt to make sure you have the right feed rate. There's also liquid feed chemical pumps. And you got a couple different types here. On the upper right, you see a peristaltic pump. And that's basically, I think of it kind of like milking a cow. You have a tube and a rotating a shaft with rollers that squishes the tube and causes liquid to be moved out. And you can see a little GIF here of how that might work. The weakness is that the tube can eventually break. We had a peristaltic pump. We had it actually at our wastewater treatment plant instead of the water plant, but uh, eventually it will wear out. It's kind of a weak point right where the tube connects to the piping where it's kind of and where the roller hits, and it will eventually wear out. You can see the wear and then kind of rotate the tube to make it last a little longer, but eventually you have to replace it. And then there's the piston pump, where it's pushing a certain amount out with each stroke of the piston pump. And normally it wouldn't be a rotating shaft that that moves the piston. It would be a magnetic or hydraulic operated piston. But as you can see, it delivers a certain amount of chemical every time it strokes, and you can set the speed and you can set the amount that is sent out with each stroke in both of these types of pumps. When you actually have the chemical entering, the coagulation chemical entering the plant, there's different ways to mix it. What the coagulation chemical needs to be mixed throughout the water very completely and very rapidly, so that by the time it gets to the next step, the coagulation chemical is dispersed and is in contact with all of the particles. It's throughout all of the water. So there's different ways to do that. The first here we have an inline mechanical mixer. You see a pipe coming down with an arrow, and it's feeding the chemical into the pipe, and then it's feeding it backwards against the flow in that pipe, and then it hits a mechanical mixer, propeller, and it's mixed into the pipe before it even gets to the basin, to the next basin. That's a very efficient way to do it. Another way is to feed the coagulant just against the flow with they call a pumped blender. Here we have a pump that's taking a little bit of water off of the supply pipe. It's combining it with the coagulant and pushing it back into the flow, against the flow. And it's allowing the flow of the water to mix it. And there could even be some static mixers in that pipe as well. And here is some examples of static mixers where you're feeding a chemical, say with a chemical feed pump, and it passes through this static auger-shaped metal or plastic in the pipe and causes the chemical in the water to change directions multiple times to allow it to mix well. And these work well. They change the direction of the water flow up to 12 times as they're doing that. And then finally, you could simply dose into a tank and have a propeller type mixer, and they would call this a mechanical mixer. These aren't going to be typically as efficient as some of these other inline mixers, but they can be designed with multiple mixers and the flow directed very carefully with baffles so that you get the best mixing possible. And I want to discuss some of the aspects of coagulation, kind of starting through the lens of alum, because alum it's kind of a general coagulant that has characteristics of all coagulants in a way, and it has also some shortcomings that will help us to segue into other issues and other coagulants. Now, almost all coagulants are pH dependent to a certain extent. Alum is often said, you read a water treatment textbook and it'll say alum works best between, and they'll give a range. In this particular reference I'm using, 4.4 to 6.0 pH range. And I've seen slight variations of that, but it's a narrow window and slightly acidic. Depending, you'll have slightly different numbers depending on the source. But why would this be? Why would alum need to be in this 4.4 to 6.0 pH range? Well, it has to do with the way the hydroxide ion, so alum is reacting with the alkalinity in the water, and it can form hydroxide ions at a lower pH. At a higher pH, it forms hydroxide particulates, which is in the form of kind of like a sticky gel. So at this low pH, it creates these hydroxide ions, aluminum hydroxide 2, and it has a little plus over it if you see these ions. So these are not particles, they're ionic. And what these are really good at is neutralizing the small organic particles, neutralizing the charge of these small organic particles. So it kind of goes one-to-one and neutralizes the charge and makes them able to be um, grown as flock and removed. And this is helpful, especially for removing organics. Those small colloidal particles of organic will go down stream if we don't remove them and cause problems like disinfection byproducts. So that's the reason to have a lower pH. So it can also help you to remove color and small colloidal particles. Those humic and fulvic acids are precursors of disinfection byproducts. Sweet flocculation is what occurs when you have a little higher pH range, above 6, and it could work between 6 and even up to 8. When you have this higher pH, alum reacts with the alkalinity in the water to form a high aluminum hydroxide precipitate, and it's kind of a dense gelatin-like flock. And so this flock then sweeps through the water, sweep flocculation. So as this gelatinous flock is settling through the water, it basically comes in contact with other particles and traps them and helps them to settle out. So obviously both mechanisms are good. So a lot of times what we'll do is we'll target a pH with alum that works best to kind of get benefit from both of these items. We have it maybe just slightly below 6 to benefit from charge neutralization, but also it's not so low where you're not going to get some sweet flocculation. So that is kind of, I hope that helps you to understand why are we saying it works better at a lower pH. And here's a couple of examples here. We have charge neutralization, and you have the aluminum hydroxide ions, and they're coming along and they're reacting directly with these charged colloidal particles, and they're neutralizing them, and they're causing them to be together. In sweet flocculation here, you have this this precipitate that's gelatinous, and it's settling down and it's capturing other particles. Captures particles as it settles, and it occurs primarily at a high pH, but there's some overlap. And so I think about these two as like the individual person going out and neutralizing these enemies, and the sweet flocculation is more like the blob that just it captures everything in its path. Alum uses alkalinity, so we may actually have to add alkalinity. And so to estimate this, if you know your alum dose, you can basically multiply the dose by about 0.5 and estimate the amount of alkalinity that's going to be used up. And alkalinity is it's the ability to resist a change in pH. And if you use up all the alkalinity, you could have a pH crash, and the pH could drop so low that it actually disrupts the coagulation process. And they measure alkalinity as equivalent to calcium carbonate. Basically, we want about 50 milligrams per liter of alkalinity in general, and we'd like to have some left over for downstream processes. We don't want to end up with zero alkalinity of water going to the distribution system. We want some alkalinity there. Normally, we adjust that by adding hydrated lime, which is calcium hydroxide, and that helps us prevent that pH drop, and also make sure that alum has plenty of alkalinity to form the hydroxides. To lower pH, there's some different methods. The most common is adding sulfuric acid to lower their pH. So if we have a pH of 6.8 and we want to get it down to 5.8, we would add some sulfuric acid to get that pH into the right range for alum to work if we're using alum. Some other types would be using hydrochloric acid. That's a strong acid, and it could be hazardous if it's not handled correctly. And also a very non-hazardous way to do it is to add carbon dioxide, which turns into carbonic acid when it reacts with water. So that's a lot safer way. Not that you want to be exposed to a bunch of carbon dioxide to breathe, but feeding carbon dioxide gas into the water at low amounts to form carbonic acid can help to lower the pH without having to handle acids. And I see Lori, we've reached the 20-minute mark.
We are there. Would you like a 5 or a 10-minute break?
Well, does anybody on the line need a 10-minute break, or would you prefer a 5-minute break? Let me know in the chat, and Lori can set the timer. Oh, we got a couple 10s. We better go 10.
Okay, that sounds good. I'm going to go ahead and start the timer, and you should be able to see it on your Zoom window. Go ahead and have a good break, and we will see you back on the other side in about 10 minutes.
Thanks, Lori.
Mhm. Okay, welcome back, everyone. I hope you had a good break. We're going to get started here.
All right, thank you, Lori. Welcome back, everyone. We were talking about alum, and I'll give you a little example here with using alum. And here is just kind of a scenario here. We have a water that has pH of 7.2. We have an alkalinity of 30 milligrams per liter in the source water. And we do some jar testing, and we're going to use alum. We're going to try to use alum, and we need a dose of about 40 milligrams per liter. And that produces the best removal when we have a pH of 5.8. So what would we do? First of all, we could estimate how much alkalinity is going to be used. And the rule of thumb is for every milligram per liter of alkalinity, it uses about 0.5 milligram per liter of alkalinity. So we could take 40 milligrams per liter, our dose, times 0.5, and estimate that we'd use about 30 milligrams per liter of that alkalinity. And the alkalinity remaining then, the original alkalinity of 30 milligrams per liter minus the amount that's used, 20, leaves us only 10 milligrams per liter. We don't have 0, but it's also too low. And we'd need to confirm this, relationship with actual jar testing, of course, too. But that's too low to depend on there not being a pH crash. Also, we would say we need to reduce our pH down to from 7.2 down to 5.8. So we'd probably have a sulfuric acid feed. And this would be the kinds of things we'd have to go through if we wanted to use alum to achieve this optimal result. And this is one of the reasons why we might consider other types of coagulants too, where we don't have to go through so much adjustment. And we'd have to confirm it with additional testing and monitor the plant performance. We would want to consider, are there other types of coagulants that aren't so pH dependent? And there's actually some coagulants that actually add alkalinity rather than using it up. And another thing that we could do, instead of having to have this high dose of 40 milligrams per liter, we might be able to improve the performance of alum by adding something like a polymer, which we'll discuss polymers in a moment. So we could actually get by with a lower dose and lower alkalinity impact by using a polymer. And polymers can actually make the activity of, or the effectiveness of coagulants work better across a wider range of pH levels as well. The PAC, polyaluminum coagulant, we mentioned before. It's a modification to alum where we add sodium hydroxide. It's a base, and that creates the hydroxides prior to dosing it. So it creates it's basically creating these hydroxides all ready to interact with particles in the water. And it works over a larger pH range than just alum by itself, impacts alkalinity less because you're already adding the alkalinity before you even dose it. And it can improve the removal of turbidity and colloids as well. And if we were just adding alum, it has to first react with the alkalinity in the water to create the hydroxides. This already has the hydroxides preformed, so but it's another treatment step before um, possibly before you actually dose. So these are the kinds of things that you could think through. Um, Another question here is, alum is the most common, most widely used coagulant, but when would we not use it? Well, just like the example we saw, we have a low alkalinity and a pH that was kind of outside of the ideal range. So you have to spend some unnecessary resources to purchase and feed and store all those chemicals. You have acid, which is a hazardous chemical. Um, Also, alum produces a lot of sludge, kind of a light feathery sludge. There might be, that might be creating an additional expense. I looked at some case studies where moving away from alum to another coagulant saved a utility about $10,000 a year just by reducing the sludge handling. Phosphorus removal, it's not that effective with alum. And so when systems have to remove phosphorus, they'll generally use an iron-based coagulant. And ferric chloride, for example, they're effective at removing phosphorus, more effective than alum. And also remember that for any of these situations, polymers can help to improve the effectiveness. So instead of moving away to a totally different coagulant or increasing the dose of a coagulant, you may be able to improve the performance just by adding a polymer. Also, we have to remember too that different coagulant choices can actually impact the downstream condition. For example, we talked about disinfection byproduct formation. If you don't get good removal, that example of the charge neutralization feature when you use alum at a very low pH, you're removing organics that could go downstream and cause disinfection byproduct problems. Here's an example of ferric chloride. Now, there's a lot of good things here we can read about ferric chloride. It's very effective at causing organic particles to clump together and so they can be removed. It functions across a wide range of pH levels. It works in cold weather. It seems like it would be an ideal type of coagulant to use somewhere like Michigan, where it's a lot colder than other places. However, there was a case that happened in Flint, Michigan, where they used ferric chloride and it resulted in some problems. They had the Flint River water that had high levels of organic matter, and they wanted to prevent TTHM formation, disinfection byproduct formation in the distribution system. TTHMs are cancer causing, and they wanted to remove those. So they chose ferric chloride. It also works in cold weather. Flint, Michigan is cold. Works across a wide range of pHs. They didn't have to adjust pH, and it's cheaper too. Seems like a win-win. However, the excess chloride in that coagulant increased the chloride levels in the water and led to the water being highly corrosive. And it not only resulted in the lead problem, but it also it used up the chlorine residuals and caused problems where some people actually died from not having properly disinfected water. Now, polymers are large molecules. They're kind of made of repeating units. The monomers are the unit, and then they're linked together chemically in a chain. There can be organic, naturally occurring polymers, and there's synthetic polymers too. But they're a long chain molecule that helps to link microflocks together to form a macroflock, to form larger flocks that will be heavier and more dense and settle better. And it also can help reduce the coagulant dosage that you need, and it can then also expand the pH range at which coagulants work. Polymers can be positively charged and function kind of like a coagulant. In some cases, systems use polymers as their coagulant, and they can also be neutral, have a neutral charge with different positive and negative sites where they'll connect with particles and flock particles. Kind of forms a bridge. There's some basic problems with coagulation. Macro problems that we can pay attention to. If the dose is too low, the flock will tend to be too small, and you won't have good turbidity removal. And you wouldn't want to wait till it gets all the way to the end in the effluent to check that. You'd want to check it, say, for example, at the end of the say the sedimentation basin. See if you're getting enough turbidity reduction there. If the dose is too high, well, you're just spending a lot of extra expense for one thing to add chemicals that you didn't need to add, but also you can get an excess positive charge that can actually cause some of these colloidal particles to restabilize. In other words, they go back to where they were before you started, and so you can end up getting high turbidity in the filter. If the pH is out of range, it can lead to poor flock formation. And if you have low alkalinity with certain coagulants, it can cause a pH drop and below the effective level of the coagulant and lead to corrosivity problems downstream. So those are the main problems. And one of the ways we can use to track how well our coagulation process is working, besides observing the settling and the turbidity, we can look at the zeta potential. And the sweet spot is just slightly negative. And what this is really measuring is it's the balance between the negative and the positive charges. We have negative charges in our turbidity in our water. There's a bunch of particles with little negative charges on them. And we add a coagulant with a positive charge. If all the positive and negative charges were equal, you'd have zero, which you would think would be the best, but it actually is best when you have it slightly negative. And this helps to promote further growth, bridging between these flock particles. They still are motivated to connect with each other instead of their charge being completely satisfied. So you can actually help to grow macro flock. So what is zeta potential? It's measured by looking at the movement of particles toward one or the other electrodes of different charges. For example, negative particles will move toward the positive electrode. Positive particles will move toward the negative electrode, and that gives you your zeta potential. So by looking at that test, it can help you to adjust your dose. If your dose was way above zero, like a +4, +5, or something like that, it would mean you probably have too much coagulant. If it's real negative, like -20, you don't have enough coagulant, probably. Of course, this is just one piece of information in the overall decision-making process, but it can be good to make quick adjustments. Let's say you have everything set right, and you're running your zeta at around a -3, and you have the dosage just right. You're getting great turbidity removal, but something changes in the source water, and the zeta potential changes as well because you're dosing the chemical at a certain rate, and there's a different amount of turbidity coming in, for example. And it would cause that zeta potential to either show higher or lower, and then you could adjust that. If it was real high, like a +5, you'd decrease your dose. If it was real negative, you would increase your dose. And we're going to try an example here, give you a chance to try this. It's kind of a thought exercise. A treatment plant, it's running along fine, but all of a sudden it begins producing excess sludge and turbidity has risen slightly. A zeta potential reading indicates +5. What adjustment should be made? And Loria, you're in charge of of the the poll.
Okay, we have about 74% right now of those have answered, so. We'll give it just a little bit more time.
How are you guys enjoying the class so far? Or guys and ladies and gentlemen, I mean, how are you enjoying the class so far? Are you benefiting from this? It's an introductory course. And so if some of you are pros, long-term pros in the water treatment industry, maybe it's a little slow for you. And if you've never seen a water treatment class before in your life, it might be a little fast. Let me know let me know if the pace is right for you so far.
Okay, so I closed the poll. And so at this point, we have 52% of people saying that A is the correct answer, reduce the coagulant dosage.
Okay. Well, 52% of you had the same answer as me. And the reason is the +5 means we have more positive charges in the water than negative. We probably have a little bit too much dosage. So the turbidity is uh, of the influent might have decreased a little bit, but the effluent turbidity might have risen slightly because we're not getting good coagulation, and maybe some of those particles are restabilizing and making it through the filter because they're small and they haven't been neutralized. Um, so I hope that was a good thinking exercise for you. There's some other factors that affect the dosage here, and we'll think about this as we kind of summarize this section here. Uh, pH makes a difference, and depending on what kind of coagulant you're using. For alum, for example, generally people are running it between 5.5 to 7.5 um, because they're taking advantage of either the charge stabilization or the sweep, or they're trying to find that sweet spot right around 5.8 or so, where they're taking advantage of both. And we have to think about that in context. If just because people are using in that range, we don't know if they're also using polymers um, and other types of adjustments to improve the effectiveness of it. We also saw that alkalinity is consumed with alum and other coagulants. And we want to make sure there's enough alkalinity in the water so that we don't have a pH drop during coagulation. Basically, higher turbidity generally requires a higher dose of coagulant. but combining it with polymers might reduce that need. You always want to make sure you do a jar test to confirm any changes before you actually initiate them. Colder water tends to slow down the coagulation process. Usually that kind of balances out because in the winter, if you're in a cold state, you probably have less water going through the process, which it gives you more time, but it could mean that you need slightly higher dose or longer mixing time. The mixing energy is also important. You want to really disperse that coagulant when it's first dosed in a rapid mix and make sure it's dispersed so that every particle is exposed to the coagulant. And then following that, you have a slow, gentle mix, and that's what we're going to look at next, flocculation. And that promotes flock growth without going so fast that it damages the particles. If we were going to calculate the dosage, we would look at three factors. If we have a liquid chemical, we would still look at what's the dry portion of that chemical. But dry chemical feed is going to be in pounds per day. The liquid chemical feed is ultimately going to be in gallons per day. And then some conversions for chemical strength if it's not 100. And I'm just going to introduce the pounds formula. For some of you are not familiar with the pounds formula, Daryl is going to go over it a little bit more tomorrow. But I'm just going to show you how we might use it. In the pounds formula, we have to have our units in very specific forms. The flow has to be in million gallons per day. So if we have 1 million gallons and 1 with 6 zeros, we would call that 1.0 mg. mgd means million gallons per day. The dosage that we use in this formula is in milligrams per liter. That is the same as parts per million. And that just like the TSS test, we measure the weight of solids in a liter of water. So we actually measure directly. And so that we also use that to express chemical dosage, milligrams per liter. And then we multiply that by the weight of water. So when we're looking at chemical feed, we're looking at it as a portion of the total weight of the fluid, really how it works. And if we have a liquid chemical, we could potentially calculate the weight of dry chemical required and then divide by the liquid weight. I'll show you an example of that, of using this. Like I say, we're not going to go too far into this because Daryl's going to explain the pounds formula tomorrow, but I'm going to show you just a quick version of how this could work. We have a plant here, a treatment plant, and it has a flow of 2 mgd, 2 million gallons per day are coming in the plant and going out the plant. And we have a liquid alum dosage of 12.5 milligrams per liter that we need. Now, the actual alum that we have has 5.48 pounds of alum in each gallon. So what should be the feed rate of this chemical in gallons per day? So first of all, I'm going to calculate how many pounds of dry alum we would need. I'm going to use that pounds formula. That flow in mgd, it's 2. The dosage is 12.5 milligrams per liter, and the weight of water is always 8.34 pounds. So if I multiply across that, 2 mgd times 12.5 milligrams per liter, that's my dosage concentration for alum, and times 8.34 pounds per gallon, I get a result that I need 208.5 pounds per day of alum, dry alum, pure alum. But now my liquid only has 5.48 pounds in each gallon, so I'm going to basically divide by the weight per gallon of the chemical. So I take that 208.5 pounds of pure dry alum, and every gallon contains 5.48, so I'm going to divide by 5.48 pounds per gallon. When I do that division, I realize I need 38.05 gallons per day. So my feed rate would be 38 gallons per day. And if I were using a chemical feed pump, I may need to reduce that down to gallons per hour so I can have the correct setting. So I might need to divide that by 24, for example, to get gallons per hour. And we mentioned mixing. We're going to talk about flocculation a little bit. Flocculation is just gentle mixing to grow the flock. You see that raw water coming in on the left? the flash mix is our coagulation step. And then we go to the flocculation basin. And we start out with higher speeds and we end up with lower speeds. By the time we get to the end, we have pretty large flock compared to what we started with. We started out with little tiny pen flock with one little tiny particle attached to one little tiny um, coagulant chemical. Uh, and then we gradually grow those larger and larger so they're large enough to settle and be filtered. And the next step that happens after this is sedimentation. So fast enough to grow, but not so fast that it damages the flock. And you see that as you proceed to the end, you have lower and lower mixing energy. The concept is you want to keep everything in suspension so that particles and coagulants are coming in contact, but not damaging the flock. And in this particular image, you see an example of a vertical mixer that might be used. There's other types of mixers. You could have a horizontal paddle type of mixer. There's an actual photograph on the upper right of your screen, and it operates the same way, paddles, and you see some walls there. In this case, it looks almost like a wooden wall there that they've placed, but there'll be some kind of baffle between each chamber, and each chamber will have a different speed. You'll start out with faster speeds, and you'll go to slower speeds, and you're trying to make sure that every portion, there's no short circuiting, so there'll be some baffles. And you see in the image on the middle right left of your screen, perforated baffle walls there where they have the dotted lines. So you're trying to prevent any short circuiting. So 100% of the flow is mixed to grow flock. You don't want any portions of the flow escaping that have not grown flock. And then it sends it to the sedimentation process. In the sedimentation process, we're using gravity to allow particles to settle. You create a zone where you have very slow velocity. The water is almost standing still to allow particles to settle out, and the sludge settles to the bottom of the basin. There's different types of sedimentation basins. We'll just look at a couple general types here. First of all, you can see a rectangular basin where the flow is going all in one direction. And you have the settled sludge. You see the inlet coming in on the upper left, and then there's the outlet going into the effluent weir. And at the bottom of this type of a basin, you might have a sludge removal system that uses an auger. They also have types that are driven chains, and I'll show you an example of that as well. Basically, we're designing the sedimentation basin so it minimizes the turbulence and velocity of water. So you have this quiescent zone. That's where most of the settling, that's where all the settling takes place. It's a very quiet area where the water is moving so slow, it's almost standing still. There's some different zones we could think about it. Where they have on this image, they have flock zone. Really, that's also the inlet zone. Usually you have some kind of baffle so that you minimize any velocity vectors going in. The settling zone or the quiescent zone is very still. The sludge zone is at the bottom, and you have some kind of provision to collect and remove the sludge. And then finally, the outlet zone, you want to have some distributed gentle flow going out once again, so you don't create any velocity currents. In a circular sedimentation basin, the water generally comes into the center, into a feed well where it's distributed evenly, and it moves toward the outside normally, where you'll have the effluent weir around the circumference of the basin. It's not always like that, but that's probably the most common, where the effluent weir is on the circumference. You can see on the kind of the lower right side of the image, you see a rotating rake. There's a rake that will rotate very slowly, and it pushes the sludge toward the center hopper, that V-shaped part of the basin where it's collected, and then there's a pump that will remove the sludge and send it to a drying bed. So it flows radially from the inside center to the outside rim. And you got that rotating rake, it's moving very slow. Generally, we can expect sedimentation basins to remove between 60 and 80%. Some sedimentation basins get up to 90% because they're optimized. Some don't do as well, but generally we can expect that. So if you took turbidity samples of your settled water, you could compare them to a standard. You can compare them to this range. Are you at the low end of the range or the high end of the range? Depends on the type of solids, how well the coagulation, flocculation process work, the design of the basin. As the water exits, it is collected in launders, which are going to carry the water to the filters. You'll see a V-notch weir. It has the dual function of helping to screen out any kind of debris that might have fallen in if it's open air. And also it can kind of indicate the flow volume. If you look at this image on the lower left of your screen, the bottom of that image, you can see that where a low water volume versus a high water volume might fall on that weir. It'll give you an indicator of what's the relative water flow. And here's a plan view and a side view of a cylindrical or circular clarifier. You can see the flow going into the center and being dispersed outward. And then you can see the effluent channel that's carrying the water ultimately to the next step, which is filtration. And the same with a rectangular clarifier. You see it coming into the inlet zone. This is a straight shot. So we have to make sure we have baffles to reduce those velocity currents, and it's flowing gently toward the effluent channels at the end and then collecting sludge at the bottom and sending it to the filters. And you can see a little bit, this is kind of blurry. I didn't realize how blurry this image was here, but you can see a little image of the sludge collecting scraper arm and the sludge collecting trough, and at the top, the launders that are collecting the water. A little different view. I wanted to bring up some concepts here. Smaller particles are going to settle slower. They have to settle before water travels from the center. Where that H was the center of a circular clarifier, for example, the particle needs to settle before water gets from the center to the effluent weir. That's how much time it has. So this diagonal line here is indicating a particle. Here we have this flow going from the center toward the outlet. How much time does that take? Well, we hope that it's longer than it takes for the particle to settle. Here's the path of a particle, the smallest particle that can settle, because it's a 45-degree angle. If we had a particle that was too small to settle, it would not get to the bottom to be settled as sludge before the water makes it to the effluent weir. So what determines that? Well, our overflow rate that we're going to calculate in a little bit is related to that. How fast water moves from inlet to outlet. Does it give us enough time for particles to settle? One way we can improve our chances of particles settling is by inclined plates, and sometimes there'll be settling tubes. They both work the same way. But these 45-degree plates, they increase the efficiency of settling. They call them lamella plates. These are inclined plates that generally at a 45-degree angle, could be different angles depending on the setup. But basically the water flows up through these, and the particles in the water are able to contact the plates, and it causes them to settle. They run out of room to roam, basically. And it's usually described as adding more surface area. But you're reducing, when you add these plates, these settling tubes or settling plates, you reduce the distance that the particle has to travel until it settles. On the right of your screen, you can see the particles there. The water still has that velocity from left to right. and they're running into that side of the plate, the right side of the plate, and their journey is over. They can no longer travel to the land of the effluent. They have to fall down and settle. And here's an example here of a tank with that same settling path. That dotted blue line is the settling path of the smallest particle, the slowest moving particle there that can settle. There's no plates, and this particle it's not settling until the very last second. It's in danger of actually flowing out of the tank. But if we add a lamella plate or a settling plate, that particle runs into the lamella plate and it settles. Settles faster too than in tank 1. So it actually just runs into the plate. And different types of sludge removal mechanisms in some rectangular clarifiers. This is a moving chain or pulley system where it's constantly rotating very slow and moving the sludge toward the sludge collection hopper. And once again, there's an image of the circular clarifier. It uses a rotating sludge scraper arm. And that sludge is going to be sent to a drying bed usually, and then transported to some kind of landfill or land applied, or that might be incinerated. Now, the overflow rate is directly related to these concepts we've been talking about. This can be expressed in a couple different ways. We're going to use gallons per minute per square foot, and generally we want our overflow rate to be between like 1 and 1.4 gallons per minute per square foot, but not too much over that. That's the general design. We might want it to be a lot less if we had a bunch of small particles that needed time to settle. You could express this in cubic feet per minute as well, and you could reduce it down to a velocity of particles or water flow in feet per second as well. But for now, just know that the overflow rate is directly related to this time allowed for particles to settle. So we're going to look at an example here of an equation. We have the overflow rate. We look at the flow in gallons per minute, and we're actually going to divide it by the area, the surface area of our sedimentation basin in square feet. So the gallons per minute per square feet. Sometimes this can be expressed as gallons per day per square foot. So we'll do an example here. We have a cylindrical sedimentation basin, and that has a diameter of 50 foot and a flow of 2,100 gallons per minute. What's the overflow rate? We already have our flow in gallons per minute, but we need to determine the surface area of the basin, and we're going to use diameter times 0.785. That's the same as pi r squared, just using diameter instead of radius. I'm going to draw a little picture here. Here's our clarifier, our cylindrical clarifier. It has a diameter 50 feet. And if I plug the numbers in, 50 feet times 50 feet times 0.785, I get a total area, surface area of 1,962.5 square feet. Now I can actually put that in our overflow rate calculation. Looks like I missed a number. I missed a 2,100, but 2,000. I'll just say we'll round it down to 2,000 gallons per minute divided by 1,962.5 gives us 1.02 gallons per minute per square foot. So that's how we would do that. And then we could compare that with our range, our acceptable range. Is it between 1 and 1.4? It is. It falls within the appropriate design range. If it was way over that range, it might mean, hey, our sedimentation basin is too small. That's it's not going to allow effective settling, and we might want to add some kind of plate or tube settlers, or get a larger sedimentation basin. I'll give you an example of how long it might take for a particle to settle. Here's a particle here. It has to settle through 10 feet of water. So this sedimentation basin has a depth of 10 feet, and it's settling at a rate of 0.013 feet per second. How much time would be required for the particle to settle? And we can look at this here. We can take our 10 feet divided by 0.013 feet per second, and it would take that particular particle 769.2 seconds to settle. We can convert it to minutes by dividing by 60 seconds a minute. So it would take a full 12.82 minutes to settle. And a lot of our basins allow much longer than that to settle. The detention time for sedimentation basins is generally between 3 and 4 hours. However, the surface area can affect how much time. For example, if you had a tank that had a ridiculous shape, it's 5 foot in diameter and it's 200 foot tall. Well, uh, that's not going to allow much settling time at all, even though it has all that extra depth. The depth is not going to help us. It's that travel time from the inlet to the outlet, or from the center of the clarifier or a circular clarifier to the outside. So the area makes a big difference. Detention time, generally we're looking between 3 and 4 hours. 4 hours gives you, more time if you have small flock and you want to make sure all the smallest particles are settling. You might need a design that gives a larger detention time, but the configuration of the sedimentation basin makes a difference too. And detention time is volume of the basin in gallons divided by the flow in gallons per minute. As you can see, the gallons on the top and the gallons on the bottom will cancel, and you'll be left with just minutes. So this detention time would give you in minutes. We'd have to then convert to hours. And here's an example here. We have a basin. It has a diameter of 50 foot. It's a cylindrical basin and a depth of 10 foot. And the plant has a flow of 800 gallons per minute. What's the detention time? And we're going to use the diameter times 0.785 again, version of the equation. I'll draw a picture here. Here's our tank again, the same diameter tank. We have to calculate the volume, we have diameter times diameter, which is 50 times 50 feet, times 0.785, that's our version of pi, times 10 foot deep. And then we have this conversion factor, 7.48 gallons per cubic foot. So when we calculate our volume in diameter times diameter is feet squared, times depth is feet to the third, or cubic feet, we convert that cubic feet to gallons because there's 7.48 gallons in 1 cubic foot. So our total equation results in gallons, 146,795 gallons. That's the volume of this basin. Now let's look at our detention time equation again. We have the volume in gallons divided by the flow. And we know our flow is 800 gallons a minute. So we're going to take our total volume and divide it by 800 gallons a minute to get the number of minutes. And here we have gallons and gallons, gallons on the top, gallons on the bottom. We're left with minutes, 183.5 minutes. If we divide by 60 minutes per hour, we get that we have a detention time of 3.05 hours. So it's right in the range here, on the lower end of the range. We also can look at the weir overflow rate. This looks at the gallons per day per length of the weir in feet. And basically what we're looking at here, we don't want the velocity at the weir to be too high where it causes velocity problems. And generally, we don't want that to go over 20,000 gallons per day per foot. So here we have a sedimentation basin. It has that same diameter, and it has a flow of 2,100 gallons per minute. And now we have the weir, it's around the perimeter of the basin. And what is the weir overflow rate? And so we're going to take gallons per day divided by the length of the weir. And is that blue perimeter of that circle there is the length of our weir, and that is the circumference. How do we calculate circumference? It's pi times diameter. And I'm just going to round off pi to 3.14 times the diameter of 50 feet. 3.14 times 50 gives us a length of our weir of 157 feet. Now, what do we need to do to calculate the weir overflow rate? It's gallons per day divided by the length of the weir in feet. So how do we calculate gallons per day? We have our flow in gallons per minute. We have to multiply that 2,100 gallons per minute by 1,440 minutes in a day. There's 24 hours in a day, 60 minutes per hour. 24 times 60 gives us 1,440. So 2,100 gallons per minute times 1,440 gives us 3,024,000 gallons per day. Now we have everything we need to calculate the weir overflow rate. 3,024,000 gallons per day divided by 157 foot of our length of our weir, and we get 19,261 gallons per day per foot. And we'll go back up to the top and compare it to what it should not exceed, and we are below 20,000 gallons per day per foot, so we're in good shape there. If we were above, it would probably mean we're applying too much water to that sedimentation basin. Now we have a pole here. A circular sedimentation basin has a circumference of 65 feet and a flow of 5,256,000 gallons per day. What is the overflow rate in gallons per minute per square foot? And there's a problem with this. Somehow there's I had a typo in this. I noticed it right off. I just did a calculation here. I'm sorry about that. The circumference should say diameter. Lori, can people do their poll over again if they want?
I think I'd have to relaunch it. I mean, we can try it if you want.
I'm not sure if everybody's okay with it. Let's try it. Only 23 people have done it.
Mhm.
And I made a big boo-boo and I wrote circumference instead of diameter. Sorry about that, everyone. I'm a typo king today. So this sedimentation basin has a diameter of 65 feet. And thank you, Lori.
Mhm.
So where you see circumference, just tell yourself that's diameter if that's possible. Sorry about that. Because it doesn't make any sense, any sense if you don't put diameter there. How is everyone enjoying the training so far? Are you learning something? Oh, I see some comments here. Okay, some people are saying it's my first water treatment. Good refresher. Good, I appreciate that. I'm gonna, this is kind of cheating here, but I'm gonna make a little change here just so we can discuss it. Diameter. And you're in charge, Lori.
Yeah, we're around 60% have answered so far, so.
You see what I do to poor Lori? I mess the
Mhm.
question all up and then tell her she's in charge.
I don't mind. Sounds good to me.
Lori is good to work, great to work with.
Mhm. We're getting there. I just don't want to rush anybody while you're doing your calculations. We'll give it just a little bit more time. Okay, I'm going to go ahead and share the results. So we had 46% of people say A, 1.1.
Excellent, excellent. So keep in mind, the instructor made a boo-boo here, and I said circumference instead of diameter. This particular slide here, I wrote in diameter. And so the first thing that I would do is convert the flow to gallons per minute, because the overflow rate, it was in gallons per day. So I take that gallons per day and I convert it to gallons per minute by dividing by 1440 to get it to a minute's time. Then I would calculate the area. If I knew that it was the diameter that was 65 feet, I would take 65 times 65 times 0.785, and I would get area of 316.6 square feet. And then I have everything I need to know for the overflow rate, 3,650 gallons per minute divided by 3,316.6 square feet of area gives me 1.1. Okay, you guys were good sports, and that's a kind of a bad typo. I didn't do it on purpose. And now we're going to move on to filtration here. And you can see a picture of a gravity filter here. There's some different layers of media, anthracite and sand and garnet. We have on the bottom with says perforated laterals. That is our collection system where we collect the clean water. And then that filtered water is sent on to the next step, which is going to be disinfection. Daryl's going to talk about disinfection tomorrow. At the top, you see those wash troughs. When we backwash this filter, that same underdrain system that's collecting the water is going to send treated clean water back up through the filter media to wash it, and the dirty water is going to be collected in those wash troughs. Some different filter concepts we want to think about. Generally, the coarser, less dense media is on the top, and there's a good reason for that. For one, it helps you to kind of separate out where you're collecting solids. The biggest particles can be collected on the top, and the smaller particles can be collected deeper down. It helps you to have a longer filter run so that everything's not having to collect at just one point. But also when you backwash, all the media is disturbed. It's all expanded. And if it wasn't organized by the highest density on the bottom, it would get all mixed up. So the highest density falls back to the bottom and the lowest density falls back on the top. Also, there's a filter ripening period. When the filter first starts working in the filter run, it has some higher turbidity. And that's called the filter ripening period because the media needs to become coated with the coagulant chemicals that we're feeding in order to be efficient at moving those very small particles. The coagulant chemical coats over the sand, for example, and then a particle comes along and it can adhere to the sand through adsorption because there are different charges. Also, there's different filter mechanisms going on. There's not only straining, but there's adsorption going on in the filter. Otherwise, you wouldn't be able to remove very, very small particles that are smaller than the pore spaces between the media grains. In general, there's different ways to stack filters. You have a single media that would just have one type of media, like sand. The filtration gravel there, it's really just support gravel to protect the under drain system and support the media. And then over on the right, you have a multimedia filter where it has anthracite coal, sand, and then garnet, which is the most dense. So these are layered because they perform different functions that allow you to extend the filter run. So the anthracite, it has the largest pore sizes, collects the larger particles without clogging the rest of the filter. The middle layer, the sand, it traps those medium-sized particles, and the bottom layer, the most dense, it captures the finest particles. And if you had a single media filter, it would tend to capture all the particles in just the top few inches, and it would become clogged. So you'd have shorter filter run. It's not using that entire volume very effectively. And they're arranged by density. Here you can see that garnet has the highest density, and it's in metric system, but 2,000 kilograms per square meter compared to the anthracite, which is much less dense, only 900 kilograms per square meter. So they're arranged in just the opposite way as they are in this table, with the most dense being on the bottom. Here's some examples here, very kind of simple examples of the different mechanisms going on. Straining is when a flock particle just won't fit between the pores spaces between two media grains. Straining. Where adsorption is you have, for one reason or another, the particles are adhering to the grains, and it could be electrostatic charge, and there's a variety of different terms that they use for this basic function, but the electrostatic environment causes particles to adhere to the media, and that's going to be improved if you have it coated with coagulant chemicals. And in general, when engineers design filter beds, they're looking at a ratio between the depth of the bed and the effective media size, or you might say the kind of like the average media size. And I have an example here I'm going to show you with a sand media. It has a diameter of a half a millimeter, 0.5 millimeter sand. And you see it's not exactly spherical, but it's that's what it looks like. It's close enough to function as a media. And the bed depth is how deep the bed is. And we're looking for a ratio between the bed depth and the media size of around 1200, give or take. That seems to give the best performance in general. Sometimes you can get away with less, but with very proprietary media and certain pre-treatment, and sometimes you might need more, but this is the general value we're looking at. I'm going to give you an example of this looking at the LD ratio for a filter that's using 0.5 millimeter sand and has a depth of 24 inches, 2 feet. But we're going to do this ratio, we're going to convert that 24 inches into millimeters. And so we take the 24 inches times 25.4 millimeters per inch. If I do that multiplication, 24 times 25.4, I get a total media depth in millimeters of 609.6 millimeters. And if I divide that by the 0.5, 609.6 divided by 0.5, we get a ratio of about 1219 or 1219.2, which is real close to this LD ratio of 1200. So that gives you a little insight on how it works. It's looking at the efficiency or the ability of the media to remove and pass water according to its size and how much depth you need, really. When you first start a filter, it has a ripening period. You see this spike in turbidity when the filter first starts. There's a little spike in turbidity, and the filter has to run a little while so that it can become coated with coagulant chemicals. It's just gotten done with the backwash. There might be a little bit of remaining debris from the backwash as well that contribute to that turbidity, but also it's not going to function well until it gets those grains get coated, and that's what filter ripening is. That there's a period that the coagulant chemicals coat the media. So there's going to be a little spike at the beginning, and you might actually run the filter to waste until the turbidity comes in to the right operating range. In this case, it looks like it took about, a minute and a half to get down to operating range. You're trying to achieve a turbidity of less than 0.3 ideally. And I mean, that spike of 1, maybe that's not as concerning because, you don't want to go over 1. But normally you would want to filter to waste until it gets within range. And then you notice at the end, around after 36 hours of filtering, the turbidity starts to increase. So it's breaking through. That filter is loaded up, and some of the turbidity is starting to come through. And so that you end the filter run and initiate a backwash. You would probably initiate the backwash based on something else like head head loss over the filter, or a change in pressure. And Lori, I think this, I'm not going to get, I have about 15 slides left. I think we can keep talking about this tomorrow. We'll end right here, and I'll include the rest of the slides in my discussion tomorrow so we can make sure everybody gets out at the right time.
Okay, that sounds good. Thank you, Greg. We did have one question. If you want to go back to your poll 3 solution slide, that Ryan had asked what the 0.785 means on that slide and where does it come from?
Okay.
And there's
Yeah,
some
good.
discussion in the chat about it.
Good question. The 0.785 is 1/4 of pi. If you take your calculator and put 3.14 and divide it by 4, you'll see it's 0.785. And that's just a version of pi that you would use when you use diameter instead of radius. The equation for area, the official equation is pi r squared. So 3.14 times radius. When you use diameter, diameter is actually radius times 2. So to make pi r squared work, you have to go diameter divided by 2 times diameter divided by 2 times 3.14. Well, those 2's on the bottom, the d over 2 times the d over 2 gives you 4 on the bottom. So you end up with d squared over 4 times 3.14. So this is just a shorthand to correct that. Does that make sense for the person who asked that? Does that make sense to you without me writing it on the screen? Let me know.
I'll keep an eye out for that response. Oh, yep, he did answer. It makes sense. Okay, well, thank you for that, Greg. And we'll go ahead and end here today, and we'll pick back up then. So if anybody has any questions that they want Greg to answer tomorrow, we'll still be looking to have some Q&A with him, and we'll finish the rest of the slides. Don't forget that you can log in with the same Zoom link that you used today for day 2. And tomorrow on day 2 is the day that you will be doing the SurveyMonkey link. So you don't have any of that work to do today. So thank you everybody for your attendance. Thank you to Daryl and to Greg. And we'll see you guys tomorrow.
Thank you, Lori. Thank you, everyone.
Mhm.
Thank you.